All right, if you've been following our workshop series, you've been watching us make some improvements to the Classroom Core login system, and I thought it'd be a good time to break down some of the math that's going on behind that system and how it makes your login more secure. So whenever you go and register for most any website, you're going to submit a username and a password to a server. Now, that username and password are going to get stored in a database. They won't store the direct text of your password, though. They're going to put it in what's called a hash. And a hash is a fantastic piece of technology. It's part math algorithm, it's part salad shooter. It will take whatever your password is or any other data, and it will sort of scramble it up, and it runs some special algorithms again, and it will produce a string of random looking hex. And hex is just a large number that's written in base 16 instead of base 10. So whenever you get to 9, 10 is A, B is 11, that kind of thing. The wonderful thing about using a hash program is that if you put the same data in, you're always going to get the same hash out. And if someone steals the hashes, it is currently impossible to run a computation against a good password hash and derive the password out of it. So it keeps your password secure. The problem is with this communication right here. So whenever you go to log in, your computer is going to transmit your password to that server. The server is then going to hash it and compare it to the stored hash that it has in the database. But anytime that it's in transit, it is insecure, and it's often transmitted in plain text. And it is possible for there to be a malicious device somewhere between your computer and the website that you're trying to connect to. This is often called a man-in-the-middle attack, and it's one of the reasons why you shouldn't connect to strange Wi-Fi whenever you're out and about. If you don't know what that device is and who owns it, then you shouldn't connect to it. One of the ways that this can be protected is through transport layer security, or TLS, or what they call SSL, or secure socket layer. And this is one of the reasons why browser makers try to get users to focus on this lock icon up in the left hand up by your address bar. That means that you're connected with some kind of transportation layer security, and it puts a layer of encryption around your data so that whenever it's sent from your computer to the server, that any intervening device, any man in the middle, or any other malicious device in the circuit cannot read your data. There are other ways that platform designers like me can make your login more secure, and we can even make it secure on a connection that isn't encrypted. And the way that we do that is we use some special math processes so that your password never actually has to leave your computer. And a hash of your password never has to leave your computer. The system that we're going to use to protect your login is based off of two mathematical features. The first one is called the Discrete Logarithm Problem. I'm not going to spell all that out, but it's based on two simple facts. The first one is that something raised to an exponent is actually fairly easy to compute, right? Even with small numbers, we can do this in our head and we get 8, right? But that a not much bigger number, if this is exponent is unknown, is actually very difficult to calculate. And so in a lot of ways, exponentiation, or raising to a power, it's almost a one-way function. It's very difficult to run a calculation to find this unknown or this discrete logarithm. And so that allows us to use raising exponents and random numbers to communicate between a computer and a server without revealing information about sort of the logins that we're trying to exchange. The other feature that we use is the commutative property of mathematics. And I'm not going to spell that either, but it basically means that as long as the numbers stay within the same order of operation, they can commute, they can move. So 2 plus 3 plus 4 is the same as 4 plus 3 plus 2, and it's the same as 3 plus 4 plus 2, and any of the other combinations that we can think of. As long as they stay in the same order of operations, then the order of the numbers doesn't matter. Now, for our purposes, that also means that something like 2 raised to the power 2, and then raised to the power 3, and then raised to the power 4 equals the same as 2 raised to the power 4, and raised to the power of 3, and then raised to the power of 2, or 2 raised to the power of 3, 4, and on my face 2. And because we use these systems, I can communicate data back and forth without the password ever having to leave. All right, so I'm going to give you a rough example of what one of these login systems is going to look like. We're going to take out a few steps. I'm going to make the numbers a little bit smaller, so if you want to, you can even follow along with a calculator on your computer or your phone, and you can work out these numbers, and you'll see how the systems arrive at the same number. Whenever a user comes in and registers, we're going to put their password through a hashing algorithm. And it's essentially going to turn your password into a large hex-based number. Now, for our purposes, we're going to hash your password to the number 5. In practicality, it would be a much larger number, and the data would be scrambled so that it would be impossible to look at the hash and then determine what your password is by trying to compute it backwards in any way. And we're going to take an agreed upon number of 2. It doesn't need to be a very big number because we're going to be raising it to exponents. And so we're going to take 2, raise it to the power 5, and we're going to get the number 32. And that's going to be what we call our verifier. And we're going to send that to our server. Now, whenever our user gets ready to log in again at a future date, they're going to send their username to the server. The server is going to then generate a random number. In this case, we're just going to generate the random number of 2. And we're going to raise our base number 2 by that random number. We're going to get 4, and we're going to send that to the user. And this is where the cool mathematics begin, if mathematics can actually be cool. Because now we can create the same number on the server and the user's computer without actually having to exchange any more data. So the user has the number 4, which is essentially 2 to this power, and because they know their hash or their password, they can recreate the hash using just client-based systems, and they can get this. And the server, because they have the V or the verifier that is essentially 2 to here, they can, instead of using 4, they use the random number that they started with, and they get these. And through the commutative property of math, we know that all of these should be equal. And in this particular case, if you want to hit your calculator and raise all these powers, they're all going to come out to this number, right? And this is just for demonstration purposes. this one here in the middle, it would be the same number. These all equal. So we now have what's called a shared secret, because if we use large prime numbers to make these calculations, it's very difficult for someone to observe them and be able to compute what the base numbers are that we're using. The only number that they can really know for sure is 2, because that's our agreed upon number, and then these numbers that they see exchanged, like this 4. And then once we've arrived at a shared secret, we can use a hashing algorithm, and we basically do a comparison, and if we compare and we show that we have the same hash based on this shared secret, that means that the user can now log in. And the user's password has never left their computer, not during the registration process, not during the login process, and not even a hash of their password has left the computer. Only thing that has left is initially we sent this verifier, which is a hash and a raising to a power, and then we exchanged some random numbers that we're raising to the power of 2 to compute these shared secrets. And that is one of the ways that we can use the discrete logarithm problem and the commutative property of math to create a login system where a user can log into the server and prove that they know the same login information that the server does without actually having to exchange or compare the passwords. And that's one of the ways that we are improving the system to help keep you safe, to keep your information private, and to make the system secure. I hope you enjoy it.